Okay, so what we're doing here is identifying this set of 8 problems here, which ones we can write single and double replacement reactions, which ones we can write complete and net ionic equations for. And yesterday I told you the only equations that we can write single and double replacement reactions for are, the only ones you can write complete and net ionic equations for are the single and double replacement reactions. So this could potentially be a double replacement reaction if it has a driving force. This could be a single replacement reaction if it has a driving force. And this could be a single replacement reaction if it has a driving force. So what we want to do is to find out if we have driving forces for these, and then if we do, we can go through the whole process of finding the complete and net ionic equation. So let's start with this one. This is a 2-part compound here in the beginning, and we have a 2-part compound here in the end. So if this reaction is going to occur, the front part of this first compound is going to join up with the back part of this second compound. And so what we're going to do is just put them together for right now. We're not going to balance it yet. We're just going to put them together. And then the front part of this last compound is going to get joined up with the back part of this. Front parts always remain front parts. Okay? So we want to know if this is going to be soluble. Since we have water around, this says it's aqueous. There is water around. And so if these are soluble, then they're also going to be aqueous. Well, your solubility rules state that sulfides are mostly insoluble unless they're bonded with something from group 1, and hydrogen is in group 1. Okay? So we're going to consider this to be aqueous. Now, just a little heads up, when you're taking AP and you're doing redox reactions, you'll assume this to be insoluble. Okay, and there's a reason for that we won't get into right now. But for this purpose, at this time, we're going to assume this to be soluble. Okay? Chlorides. Chlorides are mostly soluble. There are a few exceptions, but iron is not one of them, so this is also going to be aqueous. Since we have not formed a solid or water or anything that would give us a gas, then there's no driving force. So this reaction doesn't take place. We can simply label it as NR. No reaction. Okay? So that one's not one of our potential ones, or one of our reactions we can write complete and net ionic equations for. All right, let's go back down now to number 3. We identified that as being potentially single replacement. So a single replacement reaction has to have a driving force as well, but it's a different kind of driving force. The element that's by itself has to be more active than the element it's like in the compound. Well, this is a metal and that's a metal. Copper is a metal. So what we want to do is to see if this is going to be, if iron is more active than copper. And for this class, we're going to use the standard reduction potentials list. You could use the activity series, but in this class you're not allowed to use that on the test. You can use it for homework, but not on the test. So you need to learn to use this anyway. So what we want to know is iron more active? If it's more active, it's going to be lower on the list than the copper. So we're going to look through here, and I've got an iron 3 here, but I'm looking for the iron metal over on this side. Let's see, there's iron metal right there. And I need to find the copper now, and the copper is, where's copper? I know it's down here near the bottom. I'm sorry. It's below it on the activity series, so it's above it here. So that means that iron is more active than copper, and this is copper 2, so that'll be this one right here. This iron is more active than this copper ion, so this iron will displace this copper 2. So the iron goes over here and knocks out the copper and joins up with the sulfate. And then the copper is going to be by itself. All right, now we need to figure out the physical states here. And metals, with the exception of mercury, are, at least in this class, always going to be solids. We need to figure out the physical state of this. Most sulfates are soluble, while there are some exceptions. Iron is not one of those exceptions, so this is going to be aqueous. But we need to figure out how to balance this. Now, you could assume this is either iron 2 or iron 3. Okay? I didn't give you any rules for figuring out which one is which, so you could have chosen either one. All right, how many of you chose iron 3? Nobody? One person? How many of you chose iron 2? You don't know what you chose? Well, let's start with iron 2. If iron is 2 plus, and sulfate is going to be 2 negative, then this is balanced in that form. Okay? If that's the case, then we're ready to balance the equation. Let's hit the plus sign here. So we're going to list all of our elements: Fe, Cu, S, and oxygen, O. Make this grid we usually make. Count our elements, and we've got 1 iron, 1 copper, 1 sulfur, 4 oxygens. Over here we've got 1 iron, 1 copper, 1 sulfur, and 4 oxygens, and it's already balanced. Okay, I didn't leave myself enough room really to do the complete net ionic equations down here, but let's do that on another sheet of paper. So this is number 3, continued. So what we're going to do is going to split up anything that is aqueous and ionic. It's an aqueous salt. Well, iron solid obviously is not an aqueous salt, so we're going to leave it alone. But this is ionic. It's an aqueous salt. It's dissolved in water. So we're going to split it up. Copper has a 2 plus charge here. The reason you know that, copper could be a 1 plus or a 2 plus, but joined up with sulfate, sulfate has a 2 negative charge. Since I have 1 sulfate and 1 copper, it has to be copper 2 plus. And if it's aqueous in the compound form, it's going to be aqueous in the ionic form. And then sulfate, we said, is 2 negative. It's also aqueous, and if it's aqueous in the compound form, it's aqueous in the ionic form. Over here, we've already written out the charges for this iron. And we're going to call this aqueous. And then we've got a sulfate with a 2 negative. And then we've got solid copper because it's not an aqueous form, it's not an ionic compound, so you can't split it up. I mean, you couldn't split it up anyway, I guess. It's only copper by itself. So that's a complete ionic equation. This equation, or this reaction. Alright, so what we're going to do now is to get rid of the spectators, the things that stay exactly the same on both sides. The only thing that stays exactly the same on both sides is the sulfate. The iron changes from solid with no charge to aqueous with a 2 plus charge. The copper changes from a copper 2 ion that's dissolved in water to a copper solid that has no charge at all, that's not dissolved in water. So those have to remain, only this one stays exactly the same. So that's the one we're going to get rid of for our net ionic equation. So that's going to be iron solid plus copper 2 plus dissolved in water. And then we're going to have iron 2 plus dissolved in water over here on this side. And copper solid on this side. Okay? And that's your net ionic equation. Any questions about that? Yes? How do you know what the charge is going to be? This right here? Well, there's no any metal is going to have no charge. Okay, now that's not this. A metal is not the same thing as a metal ion. Okay, if it's just a metal, there's no ionic charge on it. That's its normal elemental form. Anything in its normal elemental form has no charge. Okay, so oxygen, for example, O2, in the atmosphere. That has no charge because it's its normal elemental form. H2, hydrogen, has no charge because it's in its normal elemental form. Does that make sense? Okay? All right, then. Now, so that's number 3. Let's see. And that's assuming you did this, assuming that iron had a 2+ charge. Let's do it with a 3+ charge now. Alright, so we're going to have iron solid. I have copper 2 sulfate. And then the iron and the sulfur over here, we have to figure out how to balance that. It'll be aqueous either way. And then copper in solid form. Okay, so if iron has a 3+ charge now, and sulfate has a 2 negative charge, then I'm going to need 2 irons and 3 sulfurs to balance the formula. So I need a subscript on the iron of a 2 here, and a subscript 3 after the parentheses for the sulfate. Now we're ready to balance this equation. So we have iron, copper, sulfur, and oxygen. Make our atom inventory grid. So we're going to have 1 iron, 1 copper, 1 sulfur, and 4 oxygens on this side. Over on this side we have 2 irons, we have 3 sulfurs, 4 times 3 is 12 oxygens, and 1 copper. The only thing we can use to balance this equation are coefficients, or leading terms, and so we're going to leave oxygen for last. We can balance either the iron or the sulfur first, it doesn't matter which one. I'm going to start with the iron just because it's listed first, it doesn't really matter. I'll put a 2 here, and that's going to give me 2 irons. Now we need to get the sulfurs balanced. If I have 3 on this side, I need 3 on this side. So I've got to go and put a coefficient 3 in front of the species. And that's going to change the number of coppers and sulfurs and oxygens. So now I have 3 coppers, 3 sulfurs, and 12 oxygens. Alright, well now we got to fix the number of coppers. If I have 3 on this side, I need 3 on this side, so I need a coefficient of 3 in front of this copper. And that's going to change only the copper to 3. Okay. Then we want to do the atom inventory. I'm sorry, not atom inventory, we did that. We want to break it apart into the complete ionic equation. And for that, we're going to break, this won't break up. We're going to have, well, we will have 2 irons now. Then for the copper sulfate, we're going to break it up into the same kind of ions we had before, but we're going to have more of them. So we do have copper 2+ in aqueous form, but if we have a 3 out in front of the equation, that means there are 3 coppers, 3 copper ions. And there are 3 sulfate ions.
Why wouldn't the iron have it?
We put a 2 in front. Is that what you mean? Okay. Over on this side now, we're going to have 2 iron ions with a 3+ charge. And it's aqueous. We're going to have 3 sulfate ions. aqueous. I didn't put the 2 negative charge here. And then we've got 3 copper metals. Okay? And what we want to do is go through and take out anything that's exactly the same on both sides. It turns out to be the same sulfate ion, and I have exactly the same number here. So when I rewrite this into the net ionic equation, I'm going to get 2 iron solid metals. I'm going to have 3 copper 2 ions. I'm going to have 2 iron 3 ions. And I'm going to have 3 copper metals with a solid here, in a solid form. Okay? Any questions about that? Yes? You have any questions about this? No? Okay. Anybody else have any questions about this? All right, then we'll go on to the next problem. You can go to the bathroom. Who's grading your paper? Okay. All right, so let's see how we're going to grade this thing. How about we do it this way? In order to get credit for it, and to keep it consistent for everybody, we're going to give a point for all of this. Let's see. So this whole thing is going to be worth a point here in the complete ionic equation. This whole thing, this, and this, and the net ionic equation. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total points. Okay? If they did it this way, it's going to come out to be the same number of points. Then it's wrong. One point. It's have to have everything that's inside the boxes. Okay?
So it was okay to use +2?
It's either one, as for the iron?
Yeah.
Yeah. Either one of those I said was fine. Based on what you know at this time, that's what you're allowed to do. Okay? Huh? Okay. So we've used iron enough now that you should know that iron has 2 different forms. Okay? You should just know that at this point. When the test comes up, if you have iron, you know you can use 3 plus or 2 plus. And the same with copper. We've used it enough. You should know copper can be 2 plus or 1 plus. Okay? All right. Now let's go on to the next problem that we could potentially have a net ionic equation for, a complete ionic equation for, and that was number 7. So we have, yes.
I did the 3 plus, but I didn't I used different numbers and I balanced it. I had a 4 and a 6 instead of a.
So if you divided all the coefficients by 2, you get the same thing?
Yeah.
All right. Then whoever's grading her paper, take off 1 point, okay, and draw one of these faces on it right here. Okay, draw one of those on there. Oh, I'm sorry, you don't have to. I'm just playing. Okay. No, this is mad.
I didn't think people frowned when they cried.
There's mad.
It's like a pumpkin.
Okay. All right, let's go on. Okay, let's go on. All right, so this is potentially a single replacement reaction as well. And zinc is a solid. We need to know if zinc will replace the hydrogen. Okay? Let's see. Where is it on here? Yeah, here's hydrogen right here. Okay? And where's zinc? Zinc's here. So zinc metal is more active than the hydrogen. Okay? So zinc will go over and displace the hydrogen. So we're going to have hydrogen over here, and zinc's going to join up with the Cl. We have to balance everything now. You need to know that this is going, whatever, if we're doing a single replacement reaction, the element that's by itself has to be in an elemental form. It can't be in an ionic form. Okay? So every time we do a metal that works out that way, hydrogen becomes H2 because that's its elemental form, and that's a gas. Okay? Zinc, it has a 2+ charge. Chlorine has a 1 negative charge, so we need 2 chlorines. So this is ZnCl. You need to know that most chlorides are soluble. There are a few exceptions. There's no exception for zinc. So if there's water around, and we're showing that there is water around because we have aqueous next to this hydrochloric acid. So if there's water around, if this is soluble, it will dissolve, and we'll call it also aqueous. Okay? Now we're ready to balance the equation. So we've got zinc, hydrogen, and chlorine. On the left side, I've got 1 zinc, 1 hydrogen, 1 chlorine. On the right side, I've got 1 zinc, 2 chlorines, and 2 hydrogens. So a number 2 in front of this species will give us 2 hydrogens and 2 chlorines. And now we're ready to write the complete and net ionic equation. Yes? You put a 2 out in front?
It's wrong. This time.
Well, yeah, supposed to must be H2. I mean, if you look right here, here's your 2 hydrogens. Okay, when they stop from being a hydrogen ion, which is in some kind of a bond with something, then you get H2. If you looked on the activity series, and I recommend that at this point that you do it with the activity series. The standard reduction potentials list, but then check your work against the activity series just to be sure. Okay, at least until the test, and then you're, getting used to both systems and getting stronger with this one. Okay, but it tells you here that H2 is the other part of this one. Okay, it lists H2 here. Okay, so let's see here. We have, for the complete ionic equation, we've got zinc metal. We have, this is dissolved in water, and an acid behaves just like the ionic compounds. That's how we start naming them, as a matter of fact. So this is going to be aqueous, and while I didn't tell y'all acids would dissolve, did I? Did everybody dissolve them? Did everybody make ions out of them? Did anybody not make ions out of them? Huh? Well, who's grading Rebecca's paper? Did she make ions out of them? Because I'm not sure I told you that. I want to make sure I give you credit for it. Did she list it like this? She did not? How did she list it? What? 2H? Two H. Well, Cl has a 1 negative charge. You have 2 of them. So in this formula right here, you have 1 hydrogen and 1 chlorine, but because I have a coefficient 2 in front, it means total I've got 2 hydrogens and 2 chlorines. Does that make sense? Okay. Yeah, I don't remember if I told you about acids yesterday or not. That's why I'm asking the question. Okay. Well, acids, because acids dissolve in water, when you put acids in water, they behave like ionic compounds. Okay? When you put acids in water, they behave like ionic compounds in the sense they dissolve in the same way. Okay? I don't know if I told you that, but I'm trying to give you credit for it if you didn't do it this way for this problem. But nobody's telling me anything, so I don't know what to tell you.
I don't think you told us,
I know I didn't. Well, I'm sorry. I don't think I told you either. You're right. But I'm just saying, if you didn't put it down this way, I need to know how you put it to know whether to give you any credit or not.
So how's it any different from any other element when you split them up?
When you don't split up the elements, we're splitting up the compounds. Is that what you mean? Okay. Well, if you didn't split it up like this, then you keep it together like that. Then you put charges on it too? Okay, then that's what you should do. That's why I was asking the question. When you do redox equations, we won't do those in this class, but when you do AP, you will do redox equations. There'll be some acids you won't break up. Okay, we're not doing that right now, but just to let you know that will happen. All right, so then over here on this side, we've got one zinc that has a 2+ charge, and we've got 2 chlorines, and that has each of those have a negative charge. And then we've got this H2 gas over here. And when we write down only what remains after we get rid of the spectators, so the only spectators are these chlorides really, and we've got a net ionic equation where we have zinc and we have 2 hydrogen ions, and over here we've got zinc ion, and we've got H2. Okay? Does that make sense? All right. So let's do that the same way we did with the other one. That'd be worth 10 points. Each one of these ions you write is worth 10 points, okay? Or each of these species you write is worth 10 points. That's what I was asking about a while ago. What doesn't have the plus or minus? On the left side? Well, it's got to be H2 here, not just hydrogen. Does she has 2 H's? Did you call it a gas? Well, she's part right, wasn't she? I tell you what. Let me come around and look at that in a minute, okay? All right. Might just be better to have you do a makeup for that. Huh? Okay. All right. Well, then it won't matter a lot. Okay. So that's worth 10 points. Huh? 20. 22? No, they're both worth 10 points. So you got a total for all of 20 points. All right.